Okay, so we're going to pick up at the end of topic 6 and we're going to talk about when is a function differentiable. So there's a couple of things that have to happen for a function to be differentiable. The first is that f of x will be differentiable at an x equaling c value if the function exists at c, so f of c exists, and the derivative at z exists. So that seems kind of like a weird definition to say it's differentiable if the derivative exists, but that means that when you do that limit process for the derivative that you get an answer. So the second thing that we look at for differentiability is that the derivative will exist at c if the function has what's called local linearity at x equaling c. So what that term means is that if you graph this on a graphing calculator or on Desmos, if you zoom in really close around that x equaling c value, so you just look at a really tiny window around x equaling c on the function, f of x basically looks like a straight line, and it specifically has to be a non-vertical line. So basically it has to have a defined slope there. Which is true of any smooth function. If you zoom in really far, it just looks like a straight line. So the next condition is that f is differentiable at x equaling c if and only if the limit as x approaches c from the left of the difference quotient is equal to some limit L, which is equal to the limit as x approaches c from the right. So the left and right-sided limit definition of the derivative have to both exist and equal the same value. So just like continuity, right? Like the function is continuous if the left and right-sided limit approach the same thing for the function. So some things to really look at for when it's not differentiable. So these are more obvious visual clues of where a function is not differentiable. A function is essentially differentiable if it's continuous and smooth at a point. So it's not going to be differentiable at x equaling c if there's a sharp turn or a cusp. So you can think of like an absolute value function. It's not differentiable if there's a discontinuity, so a jump discontinuity or a hole or an asymptote. So like there we've got like a rational function, the vertical asymptote at x equaling c. And the third thing is that there's a vertical tangent line there. So the derivative does not exist if there's a vertical tangent line, and you can kind of see that here. Right above c, it's a straight up and down line because a vertical tangent line. A vertical line is a slope of undefined, right? So the derivative is not going to exist if the slope is undefined. So we're going to use those definitions. We're going to use that, description of where a function is differentiable to determine if f of x equaling x minus 2 all raised to the 2/3 power is differentiable at x equaling 2. So if you feel like you can tackle this on your own, I encourage you to pause the video and try it and then check your work. Okay, so either you are just unpausing the video and checking your work, or you're not quite sure where to start, so we're going to do this together. So I'm going to go through all of my work. So the first thing I want to check is that the function is existing there, right? So f of 2 exists. I can plug in 2 and I get 0, right? F of 2 equals 0, that exists, we're good. So now I'm going to check my limit, limit definition of a derivative. So the derivative of f at 2 would equal the limit as x approaches 2 of the quantity x minus 2 raised to the 2/3 power minus 0. So that 0 is coming from the f of 2, right? So, and then all divided by that x minus c there, so x minus 2 in this case. So I'm just going to rewrite it. So x minus 2 is really a group in parentheses raised to the first power. So I'm dividing the same base, x minus 2. So I'm just going to subtract those exponents. So that's going to end up giving me a negative 1/3 power, so I'm going to drop that back down into the denominator. So now if I plug in 2, I get 1/0, which is undefined, so my limit does not exist. So I might want to check from the left and right. So if I check my left-handed limit, I get that it's approaching negative infinity. And if I check my right-handed limit, I'm going to get that it's approaching positive infinity. So it does not exist there, vertical asymptote in the derivative function. So f prime of 2 does not exist, which means that it's not differentiable at x equaling 2, right? Because the derivative function has a vertical asymptote there. Okay, so let's look at something else. Oh, apparently I forgot to animate this properly. That's okay. We'll look at a couple theorems and we're going to use them on that piecewise function down below. So our first theorem says that if f is differentiable at x equaling c, then f of x is continuous at x equaling c. So basically what this theorem tells us is that differentiability implies continuity. If you know the derivative value exists at a point on a function, you know the function has to be continuous there. You can't have differentiability without continuity. So the contrapositive of this is also true. So contrapositive means that you flip the if-then statement and negate both of them. So opposite statement and negate it. So that means if f is not continuous at x equaling c, then f of x is absolutely not differentiable at x equaling c. So if you know the function is not continuous at that value, you know it's also not going to be differentiable. You know the derivative just does not exist. So the super important point there is that continuity does not guarantee differentiability. So you can't just assume a function that's continuous also has a derivative at that value. And the last example that we did is actually a really great example of that, right? Because f of 2 existed, f was continuous at x equaling 2, but the derivative function was not continuous there, so it wasn't differentiable there. So what we're going to do is we're going to use that piecewise function there, and we are, for f of x below, going to determine if f of x is differentiable at x equaling -1, and I want you to also justify your answer. So again, if you feel like you can use those theorems on your own and try this and really flesh out your justification on your own, pause the video here, try it, and then unpause when you're ready to go. Okay, so either you tried it on your own, awesome, or you're super stuck and you don't know where to start. We're going to do it together then. Yeah, I didn't animate it on that page either. Okay. All right, so problem coming up for us again. Okay. All right, so the first thing I'm going to check is that f of -1, is the function going to be continuous here? So if I plug in -1, I'm going to use that top branch, so I'm going to get -3. And so now I want to know what the limit is there, right? So that means that the limit as x approaches f of x from the left is going to be -3, because from the left, I'm going to use the top branch. So now I'm going to check from the right. I'm checking my definition of continuity here, right? So as I approach from the right, I'm going to use this bottom branch, and that's going to give me a limit at -1. Well, -3 and -1 are different, which means that my overall limit does not exist. And since my overall limit does not exist, it means the function is not continuous there. So since f of x is not continuous, f of x is not differentiable, right? So if you have that it's not continuous, automatically not differentiable. That was that contrapositive that we looked at. Okay, so that's it for topic 6. We're all done.